Chapter 1.6.1 Volumes. On-disk files and containers are temporary, causing issues for applications when containers crash or are stopped. Container state isn't saved, resulting in lost files. Kubelet restarts containers with a clean state after a crash. Sharing files among multiple containers in a pod can be difficult. Kubernetes volume abstraction resolves these issues, but understanding pods is recommended. Background. Kubernetes supports various types of volumes that can be used by a pod simultaneously. Ephemeral volumes only last for the lifetime of a pod, while persistent volumes continue to exist beyond that. When a pod is terminated, Kubernetes deletes ephemeral volumes but not persistent ones. Data within volumes is retained even when containers are restarted. A volume is essentially a directory accessible to containers in a pod, with its creation, medium, and contents determined by the volume type used. To use volumes, specify them in .spec volumes for the pod and declare where to mount them in spec container strengths. Containers in a pod see a file system made up of initial image contents and volumes mounted inside. Volumes are mounted at specified paths within the image, and each volume used by a container must be independently mounted. Volumes cannot be nested within other volumes, and cross-volume hard links are not supported. Types of volumes. In Kubernetes, several types of volumes are supported, including AWS Elastic Block Store, Azure Disk, Azure File, CephFS, Cinder, ConfigMap, Downward API, Empty Dir, FC, GC Persistent Disk, Git Repo, GlusterFS, Host Path, Image, ICSI, Local, NFS, Persistent Volume Claim, Portworx Volume, Projected, Secret, and vSphere Volume. Deprecated volume types such as AWS Elastic Block Store, Azure Disk, CephFS, Cinder, Git Repo, Portworx Volume, RBD, and vSphere Volume have been redirected to the Container Storage Interface CSI drivers. A config map provides a way to inject configuration data into pods, with the ability to reference the data in a volume of type config map. The Downward API volume makes Downward API data available to applications, while the Empty Dir volume is initially empty and can be used for scratch space or holding transient data. The FC volume type allows existing Fibre Channel block storage volumes to be mounted in a pod, while the GCC persistent disk type has been redirected to the CSI driver. The host path volume mounts a file or directory from the host node's file system into a pod, but using host path presents security risks and should be avoided if possible. The image volume source represents an OCI object, such as a container image or artifact, available on the Kubelet's host machine. The ISI volume allows iSCSI volumes to be mounted into a pod, and the local volume represents local storage. The NFS volume allows NFS shares to be mounted into a pod, and the persistent volume claim volume is used to mount a persistent volume into a pod. The secret volume is used to pass sensitive information, such as passwords, to pods, and the projected volume maps multiple existing volume sources into the same directory. Deprecated and removed volume types, such as GlusterFS and RBD, have been removed entirely in recent Kubernetes releases. Overall, while there are various types of volumes supported in Kubernetes, it's important to stay updated on the deprecation and removal of certain volume types and switch to recommended third-party drivers for better support and functionality. Using Subpath. This text explains the usefulness of sharing a single volume for multiple uses in a pod by using the volume mounts subpath property. It provides an example of configuring a pod with a LAMP stack, Linux, Apache, MySQL, PHP, using a shared volume, where the PHP application's code and assets are stored in the volume's HTML folder, and the MySQL database is stored in the volume's MySQL folder. The text also introduces the subpath_expr field for constructing subpath directory names from downward API environment variables, and explains that the properties subpath and subpath_expr are mutually exclusive. An example is given where a pod uses subpath_expr to create a directory named pod1 within a host path volume, with the host directory /var/log/pods pod1 mounted at /logs in the container. The storage media for an empty dir volume is determined by the medium of the file system holding the kubelet root dir. There are no limits on how much space an empty dir or host path volume can consume, and there is no isolation between containers or pods. To request space using a resource specification, refer to the guide on managing resources. Out-of-tree volume plugins. The text discusses the introduction of out-of-tree volume plugins in Kubernetes, specifically focusing on Container Storage Interface (CSI) and Flex Volume. Previously, all volume plugins were in-tree, meaning they were built into the core Kubernetes binaries. However, with the introduction of CSI and Flex Volume, storage vendors can create custom plugins without checking code into the core Kubernetes code repository. CSI defines a standard interface for container orchestration systems to expose storage systems to container workloads, while Flex Volume is a deprecated out-of-tree plugin interface that uses an exec-based model. CSI allows for the deployment of CSI-compatible volume drivers on Kubernetes clusters, enabling users to attach or mount volumes exposed by the CSI driver in pods. Different configurations, such as persistent volume settings, driver selection, and volume attributes, can be customized by storage administrators when configuring CSI persistent volumes. Additionally, CSI supports raw block volume support for vendors with external CSI drivers and ephemeral volumes directly configured within the pod specification. For Windows Worker nodes, privileged operations for containerized CSI node plugins are supported using a community-managed standalone binary called CSI Proxy. Migrating from in-tree plugins to CSI drivers is simplified with the CSI migration feature, allowing existing PVs created by in-tree plugins to be used without configuration changes even after transitioning to CSI drivers. Flex Volume, although deprecated, can still be used with certain plugins on Windows nodes. Overall, the text emphasizes the transition to CSI drivers as the recommended way to integrate external storage with Kubernetes, and provides guidance on how storage vendors can create, configure, and deploy out-of-tree volume plugins within a Kubernetes environment. Mount propagation. Mount propagation is a feature that allows volumes mounted by a container to be shared with other containers in the same pod, or even with other pods on the same node. There are 3 different values for the mount propagation field in containers. Volume mounts: none, host to container, and bidirectional. In the none mode, the volume mount will not receive any subsequent mounts from the host or the container. The host to container mode allows the container to see any mounts made by the host inside the volume mount. Bidirectional mode behaves the same as host to container, but it also propagates volume mounts created by the container back to the host and other containers of all pods using the same volume. It is recommended to use caution when using bidirectional mount propagation, as it can be dangerous and may damage the host operating system. This mode should only be used in privileged containers, and it is important for containers to unmount any volume mounts created on termination. Familiarity with Linux kernel behavior is strongly recommended when using mount propagation. Read-only mounts. In Kubernetes v1.3 Alpha, it is possible to enable recursive read-only mounts by setting the recursive read-only mounts feature gate for kubelet and kubeAPI as well as specifying the .spec.containers volume mounts recursive read-only field for a pod. This feature allows a mount to be made read-only recursively, meaning all submounts will also be read-only. However, certain requirements must be met for this feature to be enabled, such as setting read-only to true, ensuring mount propagation is unset or set to none, running on a Linux kernel v5.12 or later, and using a container runtime that supports recursive read-only mounts. If the requirements are not fully met, the feature can be set to if possible, which attempts to enable it but falls back to disabled if necessary. Examples of container runtimes that support recursive read-only mounts include Containerd, runc, and cron. It is important to note that the Kubernetes project authors are not responsible for these third-party projects, but they provide functionality required by Kubernetes.